We're going to get more practice with trig substitution today, and in particular, we're going to focus on actually computing those integrals like we did at the end of class last time. So we have to start with our trig substitution, and then we can compute the integral. These get kind of messy sometimes. I have to be very careful to pick ones that don't turn terrible at the end, but we can do these. So we notice that trig substitution occurs usually when we have a radical where u substitution won't work nicely here. U substitution will not work in this particular problem because we would pick the stuff inside of the radical to be our u. So the x squared plus 4, its derivative is just 2x, and that 2x in the denominator, or the x squared in the denominator, will not cancel out. So we have a problem. So trig substitution will work here. So we have to start out by making our substitution. We notice this is x squared plus a number. We're in the second scenario here, so we're going to do tangent. And we notice that the square root of 4 is 2. The coefficient on the x is just a 1. So we need a 2, essentially a 2 over 1, because we would want to cancel out the 1 and keep the 2. So we've got that part. It's probably a good idea at this point to go ahead and find dx, but then do an aside to worry about the square root. So let's find dx first so we don't forget to do that. The derivative of tangent is secant squared. For these problems, you need to remember the derivative of tangent, which is secant squared, and the derivative of secant, which is secant tangent. So we're going to have 2 secant squared theta. And so if we solve for dx, this is 2 secant squared theta d theta. Okay, so now we're going to need to replace everything in our integral. I'm going to do a little aside to compute this part here, just so that we don't have a mess inside of our integral first. So let's do that part. And this is like what we did in the videos for last class. So my x is 2 tangent theta. So x squared will be 4 tangent squared theta plus 4. We factor the 4 out, and we're left with tangent squared theta plus 1. We pull the 4 out of the radical to make it a 2. Then tangent squared theta plus 1 is secant squared. So we have root secant squared theta. And so that's 2 secant theta. So that is what we will replace that square root with. So let's rewrite our integral. So we're going to have 1 over, I'll go ahead and put the 2 secant theta for our radical. X squared is going to be 4 tangent squared theta, and then we have to remember to replace the dx. So do not forget to replace the dx. This is like even more important than replacing the dx in u substitution. So our dx is this guy, so we have 2 secant squared theta d theta, and now we have to simplify. So the 2's cancel out, and one of the secants will cancel out. So we're left with a 1/4, which I'll pull outside of the integral just so that we don't have to worry about it. Secant theta over tangent squared theta d theta. And you might say, well, I don't know how to integrate that. When we get these secants and tangents in these types of problems, it's a good idea to write them in terms of sine and cosine and hope that we can deal with them from there. So secant is 1 over cosine theta. Tangent is sine over cosine. So tangent squared will be sine squared over cosine squared. And now this is 1 over cosine, and we flip this fraction. So we get cosine squared theta over sine squared theta. We notice that one of the cosines cancels out. So we're left with cosine theta over sine squared theta d theta. The beauty of this is that we can do a u substitution at this point. And this process of computing the integral, once we have it in terms of trig, this process can be messy. It can use some of our trig integral techniques from a couple of weeks ago. So this is where we just have to be careful and see what happens. But we can do a u substitution here, making u sine theta. I try a u substitution because I notice that sine and cosine both appear in here. One of them is just to the first power, so a u substitution will work great. So my du over d theta is just cosine theta, which makes my d theta du over cosine theta. And so my integral becomes 1/4 times the integral cosine theta over u squared times du over cosine theta. Cosines cancel each other out. So we have 1/4, this is u to the -2. So when I anti-differentiate that, I get 1/4 u to the -1. We have to divide by -1. And okay, so now we are sort of done. We still have some work to do though. So now we have to plug back, well, let's rewrite this as -1/4u plus c. Okay, so now we have to start plugging things back in so we can plug our u back in. So that gives us -1/4 sine theta. Okay, and you might think that you're done at this point, but if we go back, our problem was written with x's in it. Our original problem did not have thetas in it. So it would not make sense to report our answer with a different variable than what we started out with. So we need to rewrite this expression in terms of x, not theta. And this is where things can get a little funky, but hang on, it's not too bad. So the thing we need to know what we need to know what sine of theta is in particular. So this is our answer once we plug things in for theta. So the way that we figure out what theta is we go back up here to our original substitution and we solve for our trig function, so for tangent. So in this case, tangent of theta is x over 2. And now we're going to draw ourselves a nice little right triangle, put our theta in here. Tangent, we go back and remember SOHCAHTOA from pre-calc or from trig. Tangent is opposite over adjacent. So now we fill in the side. So our opposite side is x, our adjacent side is 2. Now we can find our hypotenuse. Our hypotenuse is just going to be, using the Pythagorean theorem, will end up being square root of x squared plus 4. Okay? And so now the thing that we needed to find is we needed to know what sine of theta was, because that was in our answer. So sine is opposite over hypotenuse. So that will be x over root x squared plus 4. And so if we make that substitution, we have -1/4 times x over root x squared plus 4 plus c. And you could definitely rewrite that so we didn't have a double fraction, but I think we're good stopping here with this problem. So like I said, these are messy. We're not going to be able to do too many of them in class, but just kind of make sure you can follow the process. The part of these problems that will look different from problem to problem is kind of what happens after we make that substitution. But we do our substitution, we rewrite our integral, then we do some integral magic. We get our antiderivative. Our antiderivative is going to have theta in it. So then we have to come back up here. Usually we're going to have to draw a triangle to figure out how theta relates to whatever trig function we now have. And we'll get practice in class. These will get better with more practice.